Hi folks, you are already familiar with the LTSpice UI and toolbox. In last couple of episodes, you have become familiar with the basic CMOS circuits like NOT, NAND, NOT and OR gate. In this episode, we will construct a CMOS AND gate using 6 monolithic PMOSFETs and NMOSFETs, where the PMOSFET has double the area of the NMOSFET for mobility balancing. We will apply pulsed waveforms shaped like square waveforms as the two inputs of the constructed AND gate. The two square waveforms have different on time and off time to cover all the truth table combinations of the two input AND gate. We will apply proper DC biasing and transient analysis to check the functionality and performance of the constructed two input AND gate. So stay tuned, stay focused. Hey guys, welcome back. Today we'll be constructing a CMOS AND gate, and here we will be using the monolithic MOSFETs as we are using since last couple of episodes of the CMOS circuits. And we will use two pulsed waveforms shaped like square waveform to cover the truth table combinations of AND gate. So without any further delay, let's begin. I'll double click the LTSpice, and here you can see the blank canvas of the LTSpice has been opened. I'll go ahead and click the new file icon. The new file has been opened. I'll go ahead to the file menu, click save as, and I'll save it. I'm saving the file with the name CMOS AND gate. So here is our blank canvas, and first I will place the PMOSFETs and the NMOSFETs. I'll go to the components here, and here I click on the PMOS4. Here you can see it is the monolithic MOSFET we are using, and here I'll click place. So now I'll be placing the PMOS. First, second, third. PMOS are there, and I'll right click to vanish it. I'll zoom out a bit so that I can see them together, and now at the below region I'll place the NMOSFET. I'll go to the components. I'll click the NMOS here, and again you can see this is monolithic MOSFET. The significance of the monolithic MOSFETs is that the CMOS structure can be done in a monolithic fashion in a single monolithic wafer, and we will use double the area for the PMOS with respect to the NMOS for the mobility balancing. I'll click here. I'll place the NMOSFETs. Here I place the first NMOSFET. I go downwards. I place here, and then I place another NMOSFET here. Right click to vanish it. So I'll go ahead and save the file. Now I will zoom out further. Now I will add the biasing voltage, DC biasing voltage, that is VDD. For that I will click voltage and click place. So I will click here and I right click to vanish it. Now I will do the basic wirings. I'll go ahead up to this point, go right, come up to this point, come downwards and connect with the substrate. For these three PMOS, all the substrates will be tied up to the VDD. I'm tying them up, as well as the drain is tied up to the VDD. Now for these two NMOS, we have to have a ground line. So I am drawing the ground line. I come up to this point, I move a bit further, I click here, then right click twice to make this line up to here, and we will place a load resistance here across which we will be taking the output. I click save. Now I open the wirings again, and for these two below NMOS, I have to tie the source to the ground, and also the substrate we will be tying up to the ground. Up to this we have moved in a very repetitive fashion. Now I will do the interconnection. First let me connect these points. These two are connected, these two are connected, then these two are connected, these two are connected. These two are connected. For this NMOS, the substrate will be connected to this interconnected point. From this NMOS, I'll bring a line up to this point. This will act as the input A. I'll click here, right click to vanish it, and for this point I'll click and come up to this point this will be acting like the input P, and I right click to vanish it. So these are the A and B input of the 2 input AND gate. So let me do the wirings. This is connected to this point, and this come down up to this point, get connected here. Then from this point we again connect up, and from this point we go upwards. This point, right click here. You have to place a load resistance here. Right click, vanish it, and come up to this point and connect with the load resistance. Right click to vanish the interconnection lines. Now I save the circuit. I go to the components again, and I will place the voltage for the 2 inputs. I'll click place. I connect a voltage here, and I connect a voltage. Right click to vanish it. I'll finish off the wirings. Connect it to the ground line. Connect it to the ground line. Now the one important thing is yet to be done. I will place the actual ground here, and then I will connect the ground line with the ground. I click save, and I will go for the pins. The first pin is A, and it is type input. I click OK. Place it here. I again go to the pin. I name the second pin B, and this is input. I click OK, and I will place it here. Right click to vanish it, and I go save the file. Again I will have the output A and B, and this will be the output pin. OK, and I place it here. Right click to vanish it. I'll save. I'll zoom it out a bit further, and I'll click zoom to fit. So now you can see the entire circuit. All the placeholders have been connected. Let me check if there is any wiring missing. I think all wirings have been done. Now I'll give the values to the each of the placeholder. I'll right click here, and here I will give a DC value 5 volt, and I change this name to VDD. I click OK. I click save. There are 2 more voltage sources. I'll give the pulsed voltage sources for them. So I right click here. I go to advanced, and then I click pulsed. So here the initial is 0, P on is 5, then this is 2 micro, this is 1 femto, this is 1 femto, this is 2 micro, this is 4 micro, and number of cycles is 10. So let me check the value: 0, 5, 2 micro, 1 femto, 1 femto, micro, 4 micro, 10. In the theoretical episodes, I have already explained about the pulsed waveforms. Please go ahead and watch that independent voltage source episode. There I have explained all these factors. And this is the application episode, so I will not go in the theoretical explanation. So I'll click OK, and you can see the pulse source is there. Now it's time to configure the second input. I do a right click, and I click to the advanced. I go to pulse, and again I'll set the voltages here. This is 0, this is 5, 1 micro, 1 femto, 1 femto, 1 micro, this is 2 micro, and we 20 cycles. Let me recheck the values: 0, 5, 1 micro, 1 femto, 1 femto, 1 micro, 2 micro, and 20 cycles. In theoretical episodes, I have explained about this pulsed waveform. Go ahead and watch that particular episode from this particular playlist, and I'll click OK here. So the 2 inputs are now configured. Now it's time to configure the length and width of all of the MOSFETs. I'll do a right click for this. I will give 20 micro as the length and 200 micro as the width. In case of the NMOSFET, we'll make this 100 micro so that the area of the NMOSFET becomes half. We'll keep the gate length constant. This way, we ensure that the PMOS has the double the area of the NMOSFET for mobility balancing. I'll click OK. Right click here. I click here. If in 20 micro and 100 micro, click OK. And here, and I give 20 micro and 100 micro. The all 3 PMOS are done. I'll focus on the NMOS. Starting by this, I give 20 micro as the length, and for making the area half, we will provide 100 micro for the width. Click OK. I come down to this MOSFET and do a right click, and here I will do the 20 micro, give 100 micro. I'll click OK, and on this MOSFET I do a right click, and for length I give 20 micro, and here 100 micro. Okay, now the 6 MOSFETs are configured. I'll click save. Now I'll move to the load resistance. I'll do a right click here, and the resistance value will be 100K. And I change the name to art load. So this is a load resistance. I'll click save and I'll click zoom to fit. Let me do a scrutiny. Let me bring my marker pen. So here we have VDD with 5 volt. We have input A with a pulsed waveform, and we have input B with another pulsed waveform. You can see these two are different, and they will suffice the input combination or pair of input combination of 0 and 1, so that we can verify the constructed AND gate. Now we have PMOS here, PMOS here, and PMOS here, and we have NMOS here. We have the load resistance here, and its value is 100K. And we have connected to the ground line with the ground pin. Almost everything is done, and here is our output pin is A and P. Visually everything is okay. Now we need to scrutinize by checking the SPICE netlist. So I'll clear the marking first. I'll go to view, then I'll go to the SPICE netlist. Here you can see PMOS has the correct widths and lengths, and it has double the area. For NMOSFETs, all the widths are half. Accordingly, the area will be half. For all the PMOS and NMOS, we have the 20 micro gate length. So all the PMOS has double the area of the NMOS. We have VDD 5 volt. We have load resistance 100K. We have 2 input waveforms for input A and input B. We are using the MOS models for these two, and which is coming from this .lib file from this particular path. So we have scrutinized the SPICE deck, and it looks fine and healthy. Everything is okay. Now two things are missing. One is the .IC and another is the .tran. So I'll put those two things, close it, I save it, and then I go to the SPICE directive, and here I write .IC. I have also explained in the theoretical episode what does this .IC mean and what does it do. So please go ahead, learn all those things from the theoretical episode. Again, I'll click the SPICE directive and I put a tran here. I'll click OK, and I place it here. I right click so that it vanishes. I save it, and again I go view and do the SPICE netlist. So you can see here the .IC and the .tran has came. Now I have to configure the .tran. So I'll do a right click here on the .tran, and this dialog box comes up. We will put a stop time of 10 micro start saving time, or the 0th time will be 0, from which we will start saving the data, and time step here will take 1 nano. So here you can see the .tran command has been constructed here, and it will be included in the SPICE. I'll click OK to place it here. I'll save, and here everything is done. So I click zoom to fit, save it again, and now we are ready to simulate the circuit. So I'll click on the run button. Our circuit simulation has been done, and this dialog box has opened. So here first thing I'll check, I'll go view and I'll check the SPICE output log, and looking at this you cannot find any error or warnings. This is very important for any engineer, because if any error or warning remaining in this state and we are still having the desired output, that means at next level when we are including this particular circuit as a sub block of a larger design, that time we are going to face obvious issues, right? So we have to clear all the errors and warnings from here. At least we should clear all the errors. Warnings we can decide upon case by case. And here we are done. I'll close it. The SPICE run has completed with no errors. I'll click it and close it. Now I will go and check the waveform. So first I'll probe the input A. I'll click here. The waveform comes. I click this window, hit the B from the keyboard so that another pin comes here at the bottom, and here I click on B. So B has came here. I click again the B from the keyboard, and now I will move to the right section. Here I will click on the A and B output. Now let me check the truth table. Let me bring my marker pen here. So for 0, 0 we have 0. For 0, 1, we have 0. For 1, 0, we have 0. This is a glitch is coming at this point. Please discard this because it is not holding for a time and you have to ignore this at this point. For a larger VLSI design, you have to check why this glitch is coming and what you can do to troubleshoot this. Now, 3 combinations have been checked. Now, come to the 4th. We have 1 and 1 and we have 1. So, up to this point, all the 1-0 combinations of the input AND gate have been checked. We have the proper output as per the AND truth table. We can visualize through this particular waveforms. So, our constructed circuit acting as a AND gate, and we have been successful in constructing a AND gate using CMOS structure, where we have used the PMOS area double the area of the NMOS for the mobility balancing. And we are done simulating. We have covered and all the truth table combinations and check that desired output is coming. So our construction of the CMOS AND gate is done here and we are done here. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below, and bye for today.